Ketones and aldehydes are a little bit different. They're not usually considered carboxylic acids. They're not made from carboxylic acids most of the time. And so we're going to name them a little bit differently. Again, ketones have an alkyl group on both sides of the carbonyl. Aldehydes have one alkyl group and one H, or two H's. Chemistry speaking, reactivity-wise, ketones and aldehydes are very, very similar. Ketones are just a sterically hindered aldehyde, essentially. Ketones are going to end in -one, aldehydes end in -al in IUPAC nomenclature. Again, they're not really carboxylic acid derivatives, but if some of the common ones sort of look like they are or named like it. Like esters, there's no hydrogen bonds here, so they're pretty volatile, flammable, and pretty nonpolar. Very, very important in synthesis, very important in biochemistry. We'll just scratch the surface of that in this class, and in organic too. Here are the simplest ketones and aldehydes you should know. Formaldehyde is obviously the simplest aldehyde. We could call it methanal if we were IUPAC style, because that's a one-carbon aldehyde. But pretty much everybody calls it formaldehyde because it's a kind of a formic acid derivative. In the same way, we can talk about acetone here, sort of like acetic acid, but not really. 2-propanone would be the way we would name it IUPAC style. So it's through a 3-carbon chain, and then the ketone is on carbon 2. So that's where the 2-one comes in. And here is benzaldehyde, phenylmethanal, and it is commonly used in the kitchen as almond flavoring, imitation almond extract. Okay, other aldehydes. Again, we would just kind of like count the carbons and say butanal. The newer or the older name is named after butyric acid, which is the common name for the 4-carbon thing, so it's also called butyraldehyde. But either of these are fine. A butanal is fine. Cyclopentanone here, right? So it's a cyclopentane derivative. Notice we keep the it's not cyclopentone. We keep this pentanone here. Here's a dione, so here we would bring the E back, 1,3-cyclopentane dione for 2 carbonyls. Here we're looking for the longest chain that has the carbonyl, so that's a 6-carbon chain. I'm going to give that ketone the smallest number, so it's a 3-one. So 4-methyl, 4-hexene, 3-one. E because I've got the methyl group here and my carbonyl over there, and they're E to each other. Okay, acid chlorides and anhydrides. These are going to be generally very good electrophiles, very reactive against nucleophiles, and so they're going to be corrosive. They're going to irritate your eyes because your eyes have nucleophiles in them. They're going to irritate the skin, everything like that, and they're going to usually decompose in water to yield an acid. So don't breathe them in if you can avoid it. Again, they're both derived from carboxylic acids. The two that we will see a lot and come into contact with are acetyl chloride and acetic anhydride. So again, to name this, we're essentially naming our carboxylic acid as a piece. So in that sense, it's either acetyl or, just like it would be ethanoic acid, it's ethanoyl. Just like it would be acetic acid, it's acetyl. Notice YL in chemistry is ill, so don't say ethanoyl. It's not ethanoyl, it's ethanoyl, right? Just picture there's like a little umlaut over the Y, which would be awesome, right? It would be sweet. Acetyl chloride. The other one is acetic anhydride. Again, anhydrides come from acetic acid. You can kind of picture one equivalent of acetic acid mixing with another equivalent of acetic acid and losing water. So it's an acetic acid derivative, anhydride. If anhydride sounds like you're just taking away water, yeah, that's how it works. Also called ethanoic anhydride. Almost always, there's only a few anhydrides you would ever encounter, and they're almost always symmetrical. So we only need to say kind of the one piece. We don't need to say diacetic anhydride. If we do have two different pieces, I guess we would just name them separately. But for now, we'll focus on symmetrical anhydrides, acetic anhydride being the most important, and we should know it. Okay, Acid chlorides are what we'll focus on. Is there such a thing as acid fluorides and acid bromides? Technically, there is such a thing, but they're very rarely encountered. Many of them are too unstable to really be used, and so really the most important of these is acid chlorides. So that's where we'll stick with. Again, how do we name them? We name them like we would name the acid. So this is a 2-chlorobenzoic acid derivative, but then we kind of cut it short and say benzoyl chloride. That's the acid chloride. And here, this is a trans-butenoic anhydride. It really should be trans-2-butenoic anhydride. Edit. Trans-2-butenoic anhydride. Again, derived from the acid. Okay, so now there's a big long list. You don't have to memorize it because, heck, I guess your tests are open book, open notes, so you really never have to memorize anything. Fun. Anyways, here, this is how priority works. Essentially, the more bonds to oxygen a carbon has, the more important it is. So carboxylic acids, esters get top priority. Acid chlorides and amides right below it. Whoops. Nitriles, again, kind of get lumped in that as the least important of the carboxylic acid derivatives. After that, we get to the aldehydes and ketones. After that, you get to compounds with only one bond to oxygen and then one bond to nitrogen, and then you get to alkenes and alkynes. So essentially, we can always go back to the chart if we're worried about it, but for the most part, the more bonds to oxygen you have, the more likely that group is to be kind of considered the priority, which again is what's the end of the word. So if I have an alcohol and a carboxylic acid, then it's going to be a hydroxy acid and not a acido all or whatever, right? So if I have a keto ester, it'll be an acyl ester, so acetyl acetoate or something like that. Okay, so that's how we use it. So if something loses in priority, it gets named as a substituent. And again, the bottom of the list is always alkanes and ethers. Halogen and nitro groups are always considered pieces and never the actual suffix. So just as a few examples, paramethoxybenzaldehyde. Again, methoxy is considered a group here. The root is benzaldehyde. 1, 2, 3, 4 around the ring. This is also called p-anisaldehyde because it comes from anise seed. It smells very nice, like black licorice. Here we have the formyl group. Here's a compound with a couple different functional groups. It's a benzaldehyde, but it's got a methoxy group over there, so we wouldn't really call it an ether. We would call it an aldehyde with a methoxy group. From anise seed, black licorice smelling, smells fantastic. Here, this is one of the commonly encountered amino acids, one of the 20 canonical amino acids. This is L-alanine. But if we were naming it according to IUPAC, we would call it a propanoic acid, right? A 3-carbon carboxylic acid. And there's an amine at carbon 2. So it would be 2-amino-propanoic acid. And it would be of the R persuasion because N would get 1 and this carbon would get 2. So R. Check. Sometimes it's called an alpha amino acid because the nitrogen is on what's called the alpha carbon, so the carbon right next to the oxygen like that. If you've heard of beta-alanine is the same compound, but then the NH2 is on carbon 2 like this. This is beta-alanine. Nailed it. Okay, some of you have heard this story from me, but if you haven't, here we go. So here is a common analgesic, the product of quite a bit of research to try to make a better headache pill, better than aspirin, right? This kind of looks like aspirin, but not really. If we were to name pieces here, this is the full IUPAC name, but this is not going to get your compound bought at the store, and it's hard to say. So we should come up with a better name for it. A lot of drug common names don't have much to do with the structure, but some of the older ones were pretty dependent on structure. So for instance, this one, the name of this one comes from its 3 pieces. Here this is a propanoic acid derivative. The common name for propanoic acid is propionic, and so this is kind of usually a pro will come out of that. It's their phenyl ring, and so you can use the word phen comes up a lot, right? Acetaminophen has a similar phenyl ring in there. And then this alkyl group at the bottom, it's a 4-carbon unit. This turns out to be, the old-fashioned name is isobutyl, right? Or ibu. So when you put those together, you get profenibu, or ibuprofen, which is Advil, Motrin, etc. So lots of old-fashioned drugs have this kind of thing. Acetaminophen has an acetyl group, it's an amide, so it's an acetamide, has a phenyl ring, that kind of stuff. Okay, so to summarize, here are the common compounds that you should know. I would ask you to memorize it, but again, we're not doing a whole lot of memorization stuff here. But they're going to keep coming up again and again. You might see it I might mention it in text and not draw it. So these are important compounds to kind of have as you're starting to build your chemical vocabulary. Are there other functional groups? Sure. We're not going to really focus too much on them, but we've seen some of these already, right? We've seen thiols. We've named some simple thiols before. Compounds, there's a whole lot of different sulfur things that we won't see all of them. Sulfides are compounds with carbon on both ends of the sulfur. We've seen dimethyl sulfoxide quite a bit. That's got an SO double bond. Sulfones would have 2 double bonds. Sulfonates we've finally encountered as compounds with sort of SO3, right? We'd say that's a good leaving group. That's a mesylate. And then the conjugate acid of that is a sulfonic acid. So again, we won't really have to worry too much about all these sulfur groups. Phosphine is what we call something with bonds to phosphorus. Boranes are stuff with bonds to boron. We'll start organic 2 by talking about some boranes. Silanes are the alkyl derivatives, but with silicon instead of carbon. So silicon with 4 bonds. We've already seen azide before. So azide is like nitro. It's always going to be a functional group, but it's got these weird 3 ends like this. There's a couple different resonance structures we can draw of that too. Then finally, enol. So an enol is it's when you have a OH bound to an alkene like this. And so what we'll learn next term is that that's actually not a stable compound. Enols are in fast equilibrium with ketones. And so in general, when you see an enol drawn out, that's usually not going to be a stable compound unless it's like really resonance stabilized. Okay, so again, lots and lots of functional groups that we're not covering, but lots that we are. These are the functional groups that we should be able to name now, simple versions of them anyway, mostly derived from the names for carboxylic acids in particular.